Silvanus Thompson Elementary Lessons in Electricity and Magnetism. This book was written in 1895, so some ideas and units might be outdated, but its heritage value is great. All books on my channel are in public domain. Please subscribe, like, and comment. Chapter 4. 270. Law of Inverse Squares. An important consequence follows from the absence of electric force inside a closed conductor due to a charge on its surface. This fact enables us to demonstrate the necessary truth of the law of inverse squares, which was first experimentally, though roughly, proved by Coulomb with the torsion balance. Suppose a point P anywhere inside a hollow sphere charged with electricity, figure 147. The charge is uniform all over, and the quantity of electricity on any small portion of its surface will be proportional to the area of that portion. Consider a small portion of the surface AB. The charge on AB would repel a plus unit placed at P with a certain force. Now draw the lines AD and BC through P, and regard these as mapping out a small conical surface of two sheets, having its apex at P. The small area CD will represent the end of the opposed cone, and the electricity on CD will also act on the plus unit placed at P, and repel it. Now these surfaces AB and CD, and the charges on them, will be directly proportional to the squares of their respective distances from P. If, then, the forces which they exercise on P exactly neutralize one another, as experiment shows they do, it is clear that the electric force must fall off inversely as the squares of the distances. For the whole surface of the sphere can be mapped out similarly by imaginary cones drawn through P. The reasoning can be extended also to hollow conductors of any form. 271. Capacity. In Lesson 4, the student was given some elementary notions on the subject of the capacity of conductors. We are now ready to give the precise definition. The electrostatic capacity of a conductor is measured by the quantity of electricity which must be imparted to it in order to raise its potential from zero to unity. A small conductor, such as an insulated sphere of the size of a pea, will not want so much as 1 unit of electricity to raise its potential from 0 to 1. It is therefore of small capacity, while a large sphere will require a large quantity to raise its potential to the same degree, and would therefore be said to be of large capacity. If K stand for capacity, and Q for a quantity of electricity, K equals Q over V and KV equals Q. This is equivalent to saying in words that the quantity of electricity necessary to charge a given conductor to a given potential is numerically equal to the product of the capacity into the potential through which it is raised. The capacity of an insulated body is affected by the presence of neighboring conductors. Whenever we speak of the capacity of a body, we mean of that body when isolated as well as insulated. 272. Unit of capacity. A conductor that required only 1 unit of electricity to raise its potential from 0 to 1 would be said to possess unit capacity. A sphere 1 centimeter in radius possesses unit capacity, for if it be charged with a quantity of 1 unit, this charge will act as if it were collected at its center. At the surface, which is 1 centimeter away from the center, the potential, which is measured as Q over R, will be 1. Hence, as 1 unit of quantity raises it to unit 1 of potential, the sphere possesses unit capacity. The capacities of spheres, isolated in air, are proportional to their radii. We may imagine the charge Q, figure 148, being brought nearer and nearer the sphere until it reaches the surface, then, R becomes the radius of the sphere. We may further imagine the surface completely covered with little quantities Q, so as to have a total charge Q uniformly distributed. Each little quantity would give to the sphere a potential Q divided by R. The total potential of the sphere due to the charge Q on its surface would be Q divided by R. The greater the sphere, the less would be the potential at any point in it due to the same charge Q. Thus it would be necessary to give a charge of 100 units to a sphere of 100 centimeters radius in order to raise its potential to unity. It therefore has a capacity of 100. The Earth has a capacity of about 630 millions, in electrostatic units. It is almost impossible to calculate the capacities of conductors of other shapes. It must be noted that the capacity of a sphere, as given above, means its capacity when far removed from other conductors or charges of electricity. The capacity of a conductor is increased by bringing near it a charge of an opposite kind. For the potential at the surface of the conductor is the sum of the potential due to its own charge, and of the potential of opposite sign due to the neighboring charge. Hence, to bring up the resultant potential to unity, a larger quantity of electricity must be given to it, or, in other words, its capacity is greater. This is the true way of regarding the action of Leyden jars and other condensers, and must be remembered by the student when he advances to the consideration of the theory of condenser action in Lesson 23. 273. Surface density. Coulomb applied this term to denote the amount of electrification per unit of area at any point of a surface. It was mentioned in Lesson 4. that a charge of electricity was never distributed uniformly over a conductor, except in the case of an insulated sphere. Where the distribution is unequal, the density at any point of the surface may be expressed by considering the quantity of electricity which exists upon a small unit of area at that point. If Q be the quantity of electricity on the small surface, and S be the area of that small surface, then the surface density denoted by the Greek letter ρ will be given by the equation ρ equals Q over S. In dry air, the limit to the possible electrification is reached when the density reaches the value of about 20 units of electricity per square centimeter. If charged to a higher degree than this, the electricity escapes in sparks and brushes into the air. In the case of uniform distribution over a surface, as with the sphere, and as approximately obtained on a flat disk by a particular device known as a guard ring, the density is found by dividing the whole quantity of the charge by the whole surface. Note: the word tension is sometimes used for that which is here precisely defined as Coulomb defined it. The term tension is, however, unfortunate, and it is so often misapplied in textbooks to mean not only surface density but also potential, and even electric force, that is the mechanical force exerted upon a material body by electricity, that we might well avoid its use altogether. The term would be invaluable if we might adopt it to denote only the mechanical stress across a dielectric, as in Article 279. This was Maxwell's use of the word, denoting a pulling force distributed over an area, just as the word pressure means a distributed pushing force. 274. Surface density on a sphere. The surface of a sphere whose radius is r, is 4 pi r squared. Hence, if a charge q be imparted to a sphere of radius r, the surface density all over will be ρ equals q over 4 pi r squared, or, if we know the surface density, the quantity of the charge will be q equals 4r squared times ρ. The surface density on two spheres joined by a thin wire is an important case. If the spheres are unequal, they will share the charge in proportion to their capacities, see Article 40, that is, in proportion to their radii. If the spheres are of radii 2 and 1, the ratio of their charges will also be as 2 to 1. But their respective densities will be found by dividing the quantities of electricity on each by their respective surfaces. But the surfaces are proportional to the squares of the radii, that is 4 to 1, hence, the densities will be as 1 to 2, or inversely as the radii. Now, if one of these spheres be very small, no bigger than a point, the density on it will be relatively immensely great. So great that the air particles in contact with it will rapidly carry off the charge by convection. This explains the action of points in discharging conductors, noticed in Chapter 1, Articles 38, 45, and 47. 275. Electric images. It can be shown mathematically that if plus q units of electricity are placed at a point near a non-insulated conducting sphere of radius r, at a distance d from its center, the negative induced charge will be equal to minus q times r over d, and will be distributed over the nearest part of the surface of the sphere with a surface density inversely proportional to the cube of the distance from that point. Lord Kelvin pointed out that, so far as all external points are concerned, the potential due to this peculiar distribution on the surface would be exactly the same as if this negative charge were all collected at an internal point at a distance of r minus r squared over d behind the surface. Such a point may be regarded as a virtual image of the external point. In the same way as in optics we regard certain points behind mirrors as the virtual images of the external points from which the rays proceed. Clerk Maxwell has given the following definition of an electric image. An electric image is an electrified point, or system of points, on one side of a surface, which would produce on the other side of that surface the same electrical action which the actual electrification of that surface really does produce. If the sphere is not connected to Earth, and were unelectrified before plus q was brought near it, we may find the surface density at any point by the following convention. Imagine that there are coexisting on the sphere two charges, minus r times q over d and plus r times q over d respectively. The first being distributed so that its surface density is inversely proportional to the cube of the distance from the electrified point, and the second being uniformly distributed. The actual surface density is the algebraic sum of these two. A plus charge of electricity placed 1 inch in front of a flat metallic plate induces on it a negative charge distributed over the neighboring region of the plate, with the density varying inversely as the cube of the distance from the point. But the electrical action of this distribution, so far as all points in front of the plate are concerned, would be precisely represented by its image, namely, by an equal quantity of negative electricity placed at a point 1 inch behind the plate. Many beautiful mathematical applications of this method have been made, enabling the distribution to be calculated in difficult cases, as, for example, the distribution of the charge on the inner surface of a hollow bowl. 276. Force near a charged sphere. It was shown above that the quantity of electricity Q upon a sphere charged until its surface density was ρ was Q equals 4 pi r squared times ρ. The problem is to find the force exercised by this charge upon a plus unit of electricity, placed at a point infinitely near the surface of the sphere. The charge on the sphere acts as if at its center. The distance between the two quantities is therefore r. By Coulomb's law, the force F equals Q times 1 over r squared equals 4 pi r squared times ρ over r squared equals 4 pi times ρ. This important result may be stated in words as follows. The force, in dynes, exerted by a charged sphere upon a unit of electricity placed infinitely near to its surface, is numerically equal to 4 pi times the surface density of the charge. 277. Force near a charged plate of indefinite size. Suppose a plate of indefinite extent to be charged so that it has a surface density ρ. This surface density will be uniform, for the edges of the plate are supposed to be so far off as to exercise no influence. It can be shown that the force exerted by such a plate upon a plus unit anywhere near it will be expressed, in dynes, numerically as 2 pi ρ. This will be of opposite signs on opposite sides of the plate, being plus 2 pi ρ on one side, and minus 2 pi ρ on the other side, since in one case the force tends to move the unit from right to left, in the other from left to right. It is to be observed, therefore, that the force changes its value by the amount of 4 pi ρ as the point passes through the surface. The same was true of the charged sphere, where the force outside was 4 pi ρ and inside was 0. The same is true of all charged surfaces. These two propositions are of the utmost importance in the theory of electrostatics. 278. Proof of theorem. The elementary geometrical proof is as follows. Required the electric force at point at any distance from a plane of infinite extent charged to surface density ρ. Let P be the point, and Px or the normal to the plane. Take any small cone having its apex at P. Let the solid angle of this cone be omega, let its length be r, and theta the angle its axis makes with A. The cone meets the surface of the plane obliquely, and if an orthogonal section be made where it meets the plane, the angle between these sections will be equals theta. Now solid angle omega is by definition orthogonal area of section over radius squared. Hence, area of oblique section equals radius squared times angle omega times 1 over cosine theta. So, charge on oblique section equals radius squared times omega times ρ divided by cosine theta. Hence if a plus unit of electricity were placed at P, the force exerted on this by this small charge equals r squared omega times ρ divided by cosine theta times 1, divided by r squared, or omega times ρ divided by cosine theta. Resolve this force into two parts, one acting along the plane, the other along A, normal to the plane. The normal component along A is cosine theta times omega ρ divided by cosine theta, which equals omega ρ. But the whole surface of the plane may be similarly mapped out into small surfaces, all forming small cones, with their summits at P. If we take an infinite number of such small cones meeting every part, and resolve their forces in a similar way, we shall find that the components along the plane will neutralize one another all round, while the normal components, or the resolved forces along A, will be equal to the sum of all their solid angles multiplied by the surface density, or total resultant force along A equals sigma delta times ρ. But the total solid angle subtended by an indefinite plane at a point is 2 pi, for it subtends a whole hemisphere. So the total resultant force equals 2 pi times ρ.